All right, welcome to today's Sendo Reliability webinar. This is Fred Schenkelberg, and I've gotten used to this problem with my computer crashing with moving slides and so on, so I'm hesitant to touch it right now. But if it does happen, if it freezes up, I'll be back in a couple minutes. There we go, it's working. All right, well, today's webinar is on allocation and some of my thoughts on what it means to do it well. Uh, and it's not too terribly technical. I know that there's allocation methods out there that take in all kinds of math and numbers and stuff like that. But I find that it's really not the most important part of doing allocation. And I'll hopefully explain why I think that as we go through it. Most products are a system, right? They have more than one component in it. Sometimes they have various modules and subsystems and so on. It could even be a system of systems, which is generally on the more complex end, the satellites and communication systems and ground systems and redundancies and all kinds of weird stuff going on with very high expectations for availability. Doing allocation in those gets a bit trickier in order to get a system that really works. And we tend to focus on the individual boxes or elements within the system. And I'll use the term elements a lot to mean generically some bit or part of a system. Subsystems, I tend to think of as like you buy a power supply and you stick it into your box to power whatever else you're doing with it. The motherboard might be a subsystem, the display, stuff like that would all be subsystems. They're collections of components, kind of basic stuff here. Yet it's amazing to me that a half-cent component that you can barely see, the small capacitors we use in these days, if it's in the wrong place and critical for the signal integrity of your system, and it fails or it's damaged or whatever, it can take down your whole system. Now, I've seen some allocation schemes that try to go all the way to the component level. And by and large, that's pretty fruitless and a lot of wasted energy. So we'll talk about a couple ways to get the most out of doing allocation. And by allocation, I also mean it's, breaking down the system goal to the appropriate level so that it's useful for your team. I'll try to make that clear as I can get to it. So why do we do it? So I'm going to take a sip of water and keep my fingers crossed the screen stays active here, the computer stays up. So why do we do allocation? You can drop your thoughts in chat for that. And it's not just something on the checklist we go do and nobody uses. Yeah. Yeshwant, the determined priority. That's a good one. I like that. To achieve the target. Now, doing allocation in and of itself won't achieve a target. It's a step in the way to do that, right? I agree with that, Kinesh. Which ones are critical initially? Yeah, I agree. Allocation is not the same as, say, a reliability block diagram or a system models reliability model, where we look for critical paths and stuff like that, more on more complex systems. But it can be used to look for what do we need to focus on. All right, good. So let me tell a couple of stories. And this is coming from my experience of doing over 200 assessments of different reliability programs. And I've saw some really good systems and I've seen some really bad systems. And allocation runs the gamut. It seems to be something that some reliability programs and engineers and even program managers understand and use very well. And in other cases, they just don't understand at all. It's just the concept of it doesn't work. So this is a medical device I was got called into because they were having a 50% per year failure rate for their product, their system, and they had a 2-year warranty. So overall, on average, they manufactured and shipped 3 units for every one they sold. And the 2 free ones were because the previous 2 had failed. It was a an amazing thing that they just couldn't get their reliability, system reliability, and the field reliability in order to save any money on warranty. And there were a bunch of other things that enabled that phenomena to occur for them. But one of them was they had a system goal, and it was, and I don't remember the actual numbers, but let's say it was 95% reliable over a year or something like that. I think it was actually over 2 years. But they had 5 different major subsystems, like a power supply, a compressor. There's a handful of other, pretty substantial pieces of equipment in there, and a few other minor stuff that we really didn't pay much attention to. And what they did is that each of the design teams working on procuring a compressor or, specifying the power supply or whatever, all used the system goal. They said, we need a power supply that is 95% reliable. And what was remarkable to me is that they actually achieved that. When we looked at the individual parts that they were repairing, because they did repair these and then refurbish them and ship them back out again, because they were so constrained in their capacity to manufacture new units, they had to recover as much as they possibly could. So they had pretty reasonable information about what components or subsystems were failing. And each of the major subsystems in their group was achieving about 95%. And I asked the chief engineer about it, and he goes, well, they all meet the goal. I says, well, that's the system goal. So if your power supply achieves 95%, it's taking or consuming all of the allowed failures all by itself. And it assumes that all the other systems and subsystems within your product don't fail ever. And then you can achieve your system goal. And he would kind of look perplexed. And I was like, no, we set this goal and everybody achieved it. That's okay, right? And he says, no, let's put 0.95 times 0.95 5 times, and what do you get? And in their particular example, the real number was, I think it was like 48% reliable over a year when you rolled it up with a simple series system model, which their product was a series system. And he says, that's really close to what we get back in the field. And he says, one thing, congratulations. You guys are, if you can design and actually achieve the goal, that's great. Let's do a little different math here. Let's go 0.99 for each of your major subsystems, raise that to the 5th power, and it's about 0.95 or 95% reliable. And that was his first introduction, a senior director level person doing engineering product development for like 20 years. It was the first time he'd ever run into this basic concept of the components and subsystems need to be more reliable than your system. They had no redundancy at all in their system, and the product really wouldn't be feasible that way for what they were doing. But it was the first time he ever thought that through. Very accomplished designer and project manager and stuff like that, but just unaware of allocation and how it works, or apportionment. And I also complimented him on that. When your engineering teams get a goal, they actually achieve it. It's pretty rare that people actually, by design, hit their target right off without ever measuring it or tracking it or doing anything else, because they weren't doing any of that either. But it was like, oh my gosh, how bad can it get? Well, others is they don't even have a system goal and they get what they get. But these guys took the cake for total ignorance of allocation and block diagrams and system reliability behavior and stuff like that. So that's hopefully your systems and where you work is doing way better than that. I think this sets a pretty low bar for how bad you can get. A good example, though, is I ran into one a few years ago that they did. I had a system reliability goal and they did some allocation, but they only did the allocation to their major purchased components in things like power supply, but they made their own motherboard, for example. I'm using computers generically as a system, and they bought hard drives and they bought power supplies, they bought displays, stuff like that, and they did the allocation for all of their purchased items. And it was basically driven by the procurement organization saying, hey, we need to specify reliability here so that we have can talk intelligently about how good it needs to be, and get some evidence that from the vendors that they're meeting that. And then when we have problems, we can say, compared to what we're trying to achieve and what you committed to, here's we either are or we're not doing it. So the procurement organization was actually using apportionment or allocation to fill in a gap and to create a structure to their conversations with these vendors around their reliability performance. And what was interesting, though, is that the internal design team, the stuff they did themselves, primarily, say, the motherboard, they had no reliability goals for that whatsoever. And I thought that was odd. They didn't, they worked pretty closely with their vendors, but it was led by the procurement organization. And the procurement organization said, well, we've got, half of this product and half of the bill of materials or more is stuff that we're buying, and the major pieces we're going to really pay attention to. And lo and behold, they did really well. The stuff they were buying wasn't their problems. It was really the internal ones. And that's why I was called to work with them. And he says, you've got this great system. Why don't we get the lead of procurement that's doing this modeling to actually work with you and figure out what's left over after you have all these other vendor components specified out. And it turned out that the internal design needed to be near perfect. The procurement team did the modeling and did the apportionment and worked closely with their vendors to negotiate how good they needed to be, and they adjusted goals for the other ones and so on. They had a really nice program, but they pretty much ignored the motherboard, the internally designed and built one. And so they had to carve out a little block of reliability and give it to the motherboard and start measuring it and increase the reliability requirements for the other supplied parts. And it took them a while to adjust to that system. So they had a really nice program, except for they're missing a big chunk of their product. And so it was the most unique application of either doing nothing or getting it completely wrong, or doing it really well. So they were kind of in the middle, but they were being led by the procurement organization into some good reliability practices there. A really good example. And this one was not done by a reliability engineer. It was done by a technical marketing manager, Phil, if I remember his name right. And they were starting off a new platform, a new product, and they knew from the last couple of products they rolled out that they were losing market share. They were in a tough spot. And so Phil said, well, this makes sense that if we have this system goal, then we should have, some way to set up sub goals for the other major parts. And they did it by group. There was mechanical engineering group, software group, hardware group, stuff like that. And so he set up a very simple series model, which was appropriate for their product. And said, and he came in and said, here's a simple way for us to do what some of you mentioned, is where to focus, where to allocate resources, do stuff like that. And he said, Phil said, I just made a guess based on what I know about what's been happening in the field and so on from our previous products. He said, like keyboards and mice and stuff like that, the tracking systems and the input devices are usually really reliable. So I'm going to give them 99.99% reliability as their goal. And the team that was in charge of that, one of the engineers was looking at it going, he's like, yeah, okay. And then he looked at the power supply person and says, well, overall, we want to get to 95%. So you have to be like better than that. How about 98%? And he says, oh, I don't know. And they negotiated a little bit and they put a number down. And then he got out his calculator, basically a spreadsheet, and said, all right, here's where everybody's committed to what they think they can achieve in this program. And we're at 92%, which is 3 points below our goal. And so at that point, the program manager caught on what was happening with this discussion. And she looked at the power supply person and said, what will it take to improve the reliability of that power supply? Give me 3 price points, because we got to be careful with our budget for how much this product costs and how much improvement you can provide. And you got 1 week, come back to the next meeting and give us 3 options. So they went off, did their homework, and they came back and they said, for $100, we can do this. For $500, we can do this, and so on. And they picked one of them, put it back in their spreadsheet and said, all right, we're not quite at our goal yet, but you're not the weakest link. And it was kind of like used to be a TV series as You're the Weakest Link. I don't remember what the deal of it was. And they got all the focus, but then she looked at, I think it was the motherboard, or maybe it was the CPU or memory part of it or something like that, and said, next week, come back with 3 options, trading off price for improvement. What can you do? What are the options? And so every week for I think it was a 16 or 18-week development program, every week they would get the best available estimates for all of the various parts of their system. And then each week, the weakest element of it would get the scrutiny and the focus and the resources to go make improvement. Now, a side effect of that was that everybody else was off the hook. As long as they met their committed to goal, they're okay. Long story short is the keyboard folks were never on the hook. Their product, their field history and stuff like that was pretty rock solid. They just didn't have to worry about it. But just about every other part of the system at one point or another got touched by this attention. And the side effect was that the teams that weren't on the hook that week were not asking for resources, weren't running a bunch of extra stuff to try to improve their reliability, weren't sweating out whether they're going to meet their goal or not. But as they learned more and they built prototypes and they did the routines kinds of testing and so on, they learned a lot. And they went from engineering guesses in the first meeting, just a guess based on their experience working with this product line, to vendor data and internal testing data, to accelerated life testing data, and a bunch of other information, including field data and so on, to continuously improve their ability to estimate their subsystem reliability, and hence the reliability overall. At some point, they added the feature of they called it white space. It's that the elements that were failures due to interactions between, say, a power supply and a memory or a disk drive. and they called it white space. And so they allocated some reliability to this really undefined. It's not a box you could hold. It was the pieces in between. It was all the wires and interconnects and interfaces and protocols and all that stuff. They allocated some to that. And they also allocated some for, we don't know everything. So let's give a small portion of the reliability budget to the just in case bucket. Not only did the overall program achieve the goal, it was under budget, it was on time, and when it got to the field, it actually achieved their target and the overall system goal. They ended up improving their market share. The word got out that they were back and they had their solid program again. And they did a bunch of other things to make that work. But it was one of the best examples of allocation that I've ever seen. And every week it changed. It wasn't set in stone at the start. It was used as a vehicle for discussion of where do we need to focus. And it was picked up by the program manager, and it was used by everybody in the organization as a way to focus, to make improvements, to improve their estimates of the reliability that they were trying to achieve and understanding their system. But it gave them clarity as to their progress towards achieving the overall reliability goal. And it was a very simple spreadsheet that just had all the various blocks and multiply the reliability values together. That was it. It was super simple, but amazingly effective. Now you get into more complex systems and availability type stuff. Yeah, it gets more complicated and you need better models and different, but the same basic approach can work. If everybody understands the model you're using and the way your system is broken up, then it's possible to have those discussions about what are my options to make improvements and how much do we need to improve and how much will it cost us? How long before we can achieve that? Those kinds of discussions is critical to achieving overall system reliability. Just telling the 5 groups to go off and get as good as they can is a common technique, yet it wastes a lot of resources and it puts a lot of burden on teams that really don't need it at that time. And so it's a way to, well, anyway, this example, this team that Phil had put together drove the appropriate discussions and thinking in order to achieve their reliability goal is about as good or better than most anything else I've ever seen. And it was dirt simple. And it went from guesses to better information later, but it started the discussion. And that's probably the most important thing about it. So what's the value of it? I mean, the last example I gave you is, you said, well, they achieved their goal, but it was really their, the discussions that achieve that goal. There's other tools we can use that would, do this, but what's the value of an allocation? I'll explore this a little bit here. And some of it is redundant from what you mentioned earlier. All right. One of the things I've run into is that I've run into teams that set goals and then never measure it. And then the goals are pretty meaningless. It's if you don't know where you are on the track to achieving your goals, it's hard to know what to do different. So you don't. And at times you become cross purpose. I've told the story before where these 2 folks are working on the exact same product, and one thinks the goal's really hard to achieve and gold plated everything, and the other one thought it was super easy to do and bought the cheapest components, and they're on the exact same product and the exact same circuit board. But the idea is that the goals provide us a direction, a place or a target or an objective or a direction that we're all heading towards. If it's monitored by whatever best available means we have, it gives us feedback on the way to go. I use the example, if you're going to make a handheld product that needs to weigh so many grams, well, each prototype you make or each model you make and estimate the weights and volumes and mass of all your systems, you can measure it pretty much every day. And every change, you can estimate how much it weighs. Whereas reliability, it's much more difficult to get a really good reliability figure for how it will actually perform. So it's a mix of uncertainty, from engineering estimates to field data that's almost similar components, the set that you're using, and you're making adjustments for those and so on. But the idea is that as the development team goes, part of it is getting better measures of the reliability of your subsystems and components. And it could be vendor data, it could be testing, or a mixture of all kinds of techniques. But it's regularly measured as you move forward, and as you get better information, you update that model. And that provides you feedback for the goals and for those subsystem goals with the parts, the allocated goals that you have. So the team that's working on the power supply may start with just a guess of what they can achieve. And with the focus on making improvements and making measurements of it, they reduce the uncertainty of their estimates as the program goes. And sometimes that's as valuable as anything. And at some point, I've run into it a few times where, we just can't get there from here and achieve our price point and delivery dates and stuff like that. So let's change the goal. And yeah, we're going to have to pay some more in warranty, but that it's a conscious decision versus just giving up on the goals and ignoring them. And so part of this is keeping the objective clear with, markers along the way as to, are you going to achieve it? And so the apportionment model helps that happen a whole lot easier than just trying to do it always at the system level. Another purpose or value part of it is I ran into a team, and this is kind of that okay group where they say, or we're going to have every group go off and do everybody that's working on different sub elements of the system, go try to make improvements on it. And what happened, and this is where the value is you avoid wasting resources and money, is that the software team was clamoring for more engineers because they knew that their part of the system was vital, and they needed more work to make it stable and robust and all this stuff. The mechanical team had a bunch of motors and gears and a bunch of and had to move their product. It was a delivery system in a fab complex, and they had to be relatively precise in their movements and not rattle the wafers too much and things like that, plus a pretty harsh environment in some of the system elements of the process. And they were struggling to achieve their things. So software was competing with mechanical, and the electrical guys were kind of sitting back watching the battle going on and trying to make improvements on their own, but their parts was pretty solid. They thought they were in good shape. Well, they ended up doing an FMEA, and the software guy backed off and said, all right, mechanical's got way harder problems than I got, so I'll stop pestering them for resources. But they also realized that if they did a block diagram and looked at their current estimates, it also pointed to the mechanical was critical. Software was important, yet spending a bunch of money on improving the software system would not improve the mechanical side. And the mechanical side was below the overall system targets. And so they finally came to this realization, is that we do need to prioritize where we put our money. And let's work on the 2 or 3 elements that will actually make a difference. Back to that original example of keyboards in a computer system, you could make that keyboard twice as reliable, right? Give it 6 nines reliability. and it would barely move the overall system reliability at all. It was absolutely just in the noise to start with, and making it even less noisy really didn't matter. So part of the process is a couple of people mentioned is it prioritizes. Where do you focus? And I think the good example I gave illustrates that to some extent. Program managers love it when they have a tool to allocate resources, in a meaningful way, rather than judging each plea for additional resources or time or funding or people individually, and making it part of the team discussion as you're developing it makes it clear why we're doing what we're doing. And so I've seen it work in a number of organizations that way, where it really takes a burden off the program manager to do this all in their head, basically. The other part of this, and it comes from that good story, is that it allows the team to do trade-offs. Remember that they said, the program manager said, all right, power supply, go away and give us 3 options, 3 price points and 3 abilities to improve. It allowed them to say, and in their case, it was cost of the components and subsystems they were buying in the overall system bill of material costs was an important factor for their development program. It might be time to delivery, it might be functionality, it might be something else. But by focusing on some balance, some trade-off, because you could improve that power supply to do redundant power supplies, hot swappable, and get the best possible ones you can get, all those kinds of things. The cost would go through the roof for, say, a basic desktop computer. Do we really need a redundant hot swappable things to keep the availability of that system up? Now, some would argue in some situations, especially in servers that are running your financial program for your store, you probably do want that level of cost in order to minimize the risk of downtime. But that's the program understanding their customer and their what's important to them. So set up something that balances against the cost of, if you're going to increase the cost to achieve the reliability target, is it worth it? Does it cross a line that this product now is too expensive for your target market, for your customers? And if the alleviation of risk of failures is not super dire, if you're down for a day waiting for a new power supply to show up, it's not a big deal. Well, it depends on if it's your computer or not, I guess, and how important your work that is that day. You got to trade those off. And so the idea of asking the target team that's limiting the reliability of your system to go get some options, then you can do these trade-offs. And you can do it anyway without an allocation, but this gives it a focus. And it says, if we can improve the reliability, we're going to have to either change the design, which may take longer, or it's going to cost more or something, or it's a risk. We don't know if it'll work or not if we change it. Those all can be discussed as to then what are the other options. So if I need like 1/10 more reliability out of something, what if the next 2 pieces on the Pareto of least reliable each improved a little bit? Could I make it up somewhere else? And so it becomes a bit of horse trading to some extent as to what do we need to focus on in order to meet the overall system goal. And it allows lots of trade-off discussions to occur. So it enables that to occur, is one way to say it. All right. Well, I can't go through this webinar without at least explaining how to do this. And I have a couple of simple methods I've seen over the years, and some I've used myself to some effect, I would say. I walked into a team, and I'll use the example of a computer for keep it generic, and introduce the idea of doing allocation. They had a system goal, and they hadn't done allocation or apportionment. They kind of knew the concept. I didn't have to teach them about the math of basic reliability and how it works in a series system. And they really didn't have a great amount of field data or background information. They weren't a startup, they weren't brand new, and the engineers were reasonable folks, and they were kind of hemming and hawing and not sure and how to do this stuff. So I just got on the whiteboard and I said, all right, what are the subsystems you got? Straight line series system, you got a motherboard, power supply, hard drive, so on, 5 subsystems, and you want to achieve 95% reliability. And at that point, I said, for their product, they had a couple more systems and other stuff, but I use this 95% 5 subsystems because I can remember the math. I said, how about we just put 99% reliable over this duration for every subsystem? And they all looked at me like, it's that simple? Why were we thinking this is much more difficult? And I says, well, you got to start somewhere. And I saw the keyboard folks were like, oh, piece of cake, no problem. But the power supply folks were like, wait a second, I don't know if I can meet 95%. Just simply putting a straight line model up there, just saying everybody has to achieve 99%. It immediately started the discussion. It was a key part of that number, that really great example, is that the power supply folks said, I don't know if I can meet 95% or 99%. Well, do you just don't have an estimate, or do you have evidence that you can't meet it? And how good can you get? And they said, well, I don't know. I got to go do some, work and go figure it out. And they came back and they said, I think we can meet 98%. Okay. So then I looked at the rest of the team, and the program manager said, all right, which one of you is better than 95% that can make up this 1% we need? Power supply people said, yeah, we can do that. They don't think they had any data except history of that it's almost never on the field failure program in systems and their experience with it. So they gave up just enough so that overall they meet the goal. I think they were playing their cards close to their hand. But the discussion continued like that, starting with a straight line allocation, and then who can commit to that? What's your evidence that you can actually achieve that? And if you couldn't achieve it, then what are our options? And the program went on like that, and eventually they achieved their goal. But it was a bit of negotiating as they went. It's a different technique also, so I don't want to get ahead of myself. Now, the other one is, especially if you've been making a product for a while, or you have reasonable field failure data, those kinds of things, is use that data. Use what you know. Use the engineering knowledge you have. Use the field data that you have. Use the internal testing. Use your vendor data. Get the best available information that you have readily available as you're starting a program. And then it gives you a baseline as to what you could achieve, right? You already have concrete examples, especially if you're using lots of field data. And it says, if we add up everything that we already know and we're already doing on our previous products, it gives you a reasonable estimate of what you're going to do in the new one. Then you only need to focus on what's new. And this is a common method. Even if we don't call it apportionment, we say 90% of our design is exactly the same. We have a new element here, these new features and functions, and a new vendor for this part. Well, let's focus on those and get a better estimate of them and see how we do overall. But it also gives you a check step on your system goal, because this is what you're already doing. And you already know a lot about how things fail. So if you want to improve the reliability performance, say to reduce warranty or improve customer satisfaction, then you can use that information to get an estimate of, well, how much better can we get? So if I know that the power supplies are failing with this kind of types of failures that's occurring, and we redesign the power supply or purchase a better one that avoids those failure mechanisms, those failure modes, we can strip those out of the estimates for the power supply, and it gives us an improved reliability performance. And it's that kind of what if type thing is an example of where a simple model helps you a lot, not just for reliability, but for all kinds of different scenarios. But it gives you an idea of, one, where you are based on your best available data, but also what's possible. So if I know the power supplies fail for X failure mechanism and it accounts for 5% of its failures, well, let's do a little bit of math and figure out, well, how much reliability improvement is that if I get rid of 5% of the failures? Is that enough to be confident that we can improve the reliability, the system reliability goal? So as the individual subsystems and components are known to be better than your, and when collectively put together, are better than your system goal, well, should we improve the goal or just leave a little margin there? That's usually a good spot to put in a block for the unknowns. And if we do better than we expected, we'll deal with that problem later. Although, as an aside note, years and years ago, I was working at Hewlett Packard at a corporate group, and we were looking at individual divisions' warranty numbers. And the CEO at that point was on an internal meeting, really focused on that we needed to be consistent. If you say you're going to ship 1,000 units and you're going to have this much profit, you need to actually do that. And variations to where you make too much money, or variation where you make too little money because you miss your targets, those are all bad. And she was looking at it more from a Wall Street and investors' point of view. So the team I was in knew a handful of those divisions were missing their targets because in one case, their product was way better than they expected on a reliability point. And they set aside way too much money into warranty accruals. And so that was money tied up. It wasn't in profit. And they eventually moved it to profit, and then they had too much profit compared to where they expected to be. Vice versa, and unfortunately more common, is the product goes out and it's worse than we expected, and we burn through more profit warranty than we expected. And so we made a study. I think we had 48 divisions that we had access to their data, and there were about 10 that were on target for the year, and about 40%, 50% were missed because their warranty was too low, and others missed because their warranty was too high. And a handful were missed because of just really bad understanding of their market. They didn't sell as many, or they sold way more, but their warranty was pretty accurate. And so we made the point that if you wanted to be consistent, you had to be hitting your reliability targets. And the same goes when we do apportionment. It's hitting the target is the key part. If you go over on your target, and it's a key part that attributes to your field failures, and you inadvertently really reducing your field failures more than you expected you would, that may have a financial hit for the people tracking the overall ability to hit your numbers, hit your targets. So as soon as you know that's happening, let the senior folks know and the financial folks know so they can adjust their forecasts. Complete aside from doing apportionment. And the last one, very simple method, is just ask the various groups. that are responsible for contributing a major element of your system, how good are they going to be? And then track them, and then start that discussion about trade-offs and so on. The design team, engineers in general, and the collective team putting together a new product, tend to know quite a bit about what works and what doesn't work, and what will be a problem, or where the areas of uncertainty will be. And so from those negotiated parts is you end up with a set of estimates for your system, and you can determine whether or not you're going to achieve the overall goal, and start that whole process of where to focus and so on. Oftentimes is you also need to ask, or what I often do is then also ask, well, how sure are you? What's your evidence? Right. And if they've got solid information, say from field data or from, the internal testing or whatever method they're using, if it makes sense and they're really sure that they're going to be at 97.5% reliable, cool. We don't need to spend more money getting a better estimate. Whereas if they say, well, this is all brand new to us, we kind of think it'll be maybe, they kind of go shrug their shoulders and go 98%, give or take 5%, we just don't know. And like, okay, let's invest in getting a better estimate. And that allows that team to hone how well they know whether they're going to achieve their particular goal or not. As opposed to making an improvement, sometimes we just need a better measure of how well we're doing. And so it allows us to understand not only the number, but also the uncertainty around it. And sometimes in reducing that uncertainty is the right activity to take on. All right, I think that's all I got there. So will this work in your organization? I think I've kept this the last 3 or 4 months because I kind of like this question. Will this work for you? All right. Now that's just my thoughts on and my experience with using apportionment. Now you can get into mill standards and all kinds of other WYSIWYG stuff and get super elaborate models and weighting of this and that and the other thing. And I found that that's a great exercise. And about that's all. If the rest of the team doesn't understand it, if they're not bought into it, if they're not going to talk about it, if it doesn't affect their budgets and focus and whether they're going to make improvements or not, it's just an interesting report. And that's about it. Pretty much no value whatsoever. But if it's built into your organization's discussions about how do we achieve the goal, then it's immensely valuable. So even a very, very simple straight line method can get that conversation started. So what do you think? What works for you guys? What's your takeaways on this one? All right. I think I either lulled you all into sleep or it is just really clear. I'm not sure. Uh, I do know that next month, I actually looked it up. Chris Jackson, or not next month, in 2 weeks, Chris Jackson's doing the one that we had to cancel because he was just in a sick bed. He had a pretty bad flu, I think. With it's about confidence is about you. He's going to explain that a little bit. The idea of confidence and confidence intervals and how to think through about those a little bit differently than the statistical calculation of them. But what does it really mean as we make decisions? All right, so I'll stay in the line if there's any other comments or questions, and it will end a little bit early this month. I have no idea what I'm talking about next month myself, but we'll figure it out as we go. Thanks everybody for joining today. Oh, got a quick question or thought here. In my experience, it's often challenging to support the allocations using data since everyone looks at data at data to support. Well, that's, yeah, there's a spectrum of everything from an engineering guess to, physics of failure modeling for the major components that cause your failures. It's a combination of understanding where that numbers come from and how well they represent reality and how well other people understand them. So we can do really wizard science, and if nobody understands it, they're not going to use it. So I find that the simpler the better, as long as we're moving in the right direction in achieving the overall goal. But the using all kinds of fancy math and weighting and all these various technical methods for doing it, I find less than useful. It's much easier to say, you know, um, Mohammed, you got the power supply. What do you think it's going to be able to achieve? And Jill, you're working on this circuit board. How good is it going to be? Here's the reliability, the performance criteria we're looking for. Will you meet that? And that it's more important to get the conversation going and where to focus resources than it is to get it right. The allocation should always be flexible. It's not set in stone. It should never be set in stone. It's what's possible versus what's the impact of that possible and what's its overall influence on the system reliability. So follow-up question is, does the allocation activity really add value if the design choice is already finalized? Does the allocation influence the testing needs in any way? It's a good question. If the design is already set, then the allocation process is pretty mute, right? If you're not willing to change part of your system, then modeling and allocation and all that stuff is immaterial. It doesn't make any difference. Doing a allocation in that case would have no value whatsoever. And it's the same if you're going to go do testing, but you're not going to change the design. Well, why do testing? I've run into that a number of times where they get to their final prototype, then they say, oh, we got to do some testing. This is, are you going to change your design? No. Then why are you spending all this money doing something that is going to have no impact on whether you ship the product or not? Well, it's just in case. Have you ever used any information from your testing to delay a program or make a change? And no. This was the answer I got. And it says, well, stop doing the testing. If you're not going to use it, what's the point? Now, allocation in the way I think of it is when it's done well, helps you reduce the uncertainty of your estimates for that particular component or particular subsystem. And it could be the vendor doing the testing or you doing the testing or a combination, but it's focused on answering that specific question. Is this power supply at 98% reliable or not? And how accurate do you need to know that answer? And it depends on your team and so on. But the idea is that the testing should be to answer a question. And the discussions around allocation and are you achieving your system goal may well point to that you need to understand it better. And so do an accelerated life test or get the field data and do the analysis, do something that improves the accuracy of your estimate. And that may well be testing, but it doesn't come about until you have that trigger, that comment that you need to know that answer. So I don't like just doing testing just because we do testing. It usually adds little to no value whatsoever. How about what during the design process we say, we're not really sure about this component when it is in startup condition and how does it behave? Well, let's make a mock-up for that circuit and see what it does in startup surge power, going into it. Does it fail? What are the risks that we're looking for? How do we measure that? What kind of degradation are we trying to monitor? Those kind of things. So testing is not, it's like allocation. It's not set in stone at the start. It's what do we need to know? What questions are we trying to answer? In the discussions around allocation is a way to direct some of that testing, but not, it may be other activities that feed into the overall model. Good, good. Thanks, Carl. Thank you. Thank you. All right. Like I said, I'll stay on the line if there's any other comments or questions, but I'll go ahead and pause the recording.